Hi ladies and gentlemen, in the previous videos you understood the quantization, and there you saw that the steps were uniform. You understood the uniform quantization. Now in this video I will tell you about the need for a non-uniform quantization and the concept of companding for speech signals. So let me start with that presentation. So the speech is organized into your learning outcomes, overview of non-uniform quantization, then A-low companding, mu-low companding, and the summary of understanding. So in this session you will learn the need for non-uniform quantization, then you will learn the A-low and mu-low companding rules. Then you will observe the two combander transfer characteristics with a Python demo. Then you will understand the practical difficulties in the hardware realization of these two transfer characteristics or these two companders. Then in the end you will appreciate a piecewise linear approximation for the companding characteristics. The linear quantization method that employs uniform quantization levels, that method is often very disadvantageous, especially with the speech signals. Because in speech signals, both the small amplitude signals and large amplitude signals are equally important. So a uniform step for both small and large signals is not very advantageous, because sometimes we may completely skip the small signals. Sometimes large signals may skip over or span over more than one step that way. So employing the same step for both small signals and large signals is not advantageous. So a better method is to employ a non-uniform quantizer that assigns small quantization levels to small amplitude signals and big quantization levels to large amplitude signals. The scheme actually compresses large signal swings and expands small signals, results in compressing and expanding. So that the term companding came through this compression and expansion. There are two standards for companding, that is A-low companding and mu-low companding, depending on the transfer characteristics, and countries used also. So when you look at the A-low companding, if the input is the input-output relation of an A-low compander with the input X and output Y, normally usually this X is the speech signal input, usually it is normalized to unit amplitude. So this Y, or it is normalized to some value, so Y is A times mod X by log 1 plus A into SGN X for values of input from modulus value between 0 and 1 by A. Now this SGNX is a sign function. It is positive for positive X and negative for negative X. So when the value of the input X is between 0 and 1 by A, it is the signum function into A mod X by log 1 plus A. That these are small amplitude values. For large amplitude values, that is from 1 by A to 1, modulus value of input from 1 by A to 1, this value is SGNX into 1 plus log A mod X divided by log 1 plus A. A is a parameter in this law. So typically A is 100. We will see a demo of these characteristics. We will run a Python code, and we will appreciate this transfer characteristics for different values of A, like 75, 89, 100, etc. So I will show you that code. This is a A-low companding code. Here I have imported the SciPy and PyLab modules, and in of course I read a wave file. Okay, I read a wave file here. In my directory I have a wave file. How do I read in this wave file? I read it using a module called wave file with E missing, WAVFILE. It is imported from the scipy.io module. So I have a file stored tunc.wave in my directory. I read this, okay, Then what I do is I write a function for this ALO companding. That is, suppose this is a function of the input signal x and the parameter a. So x1 is the array of float values. I convert this x, whatever is read into this function, I convert into float values. Then I initialize another array, a blank array. Then the normalization is done here. Whatever input is coming here, this is divided by the maximum value of that function, so that all the x is normalized to plus or minus 1 within that range. The magnitude is always below 1. So for all those values in that x-norm function, if this absolute value of I is less than 1 by a, this is the low amplitude signals, y is this sine function into a absolute value of I into log 1 plus a, 1 by log 1 plus a, that is I by log 1 plus a, that is mod x by log 1 plus a. Else, if this value is greater than 1 by a, then I have another function, the signum function into a into 1 plus log a mod x divided by log 1 plus a. Then this value, whatever y, this is appended to my y array. Okay. So what I do here is I read a speech signal, then I take the that input signal and I apply to this combander. Then I have to write it back and appreciate this wave file. Okay, after combining, what will happen to that wave file? I'm very interested in that. So for that, I have to know the rate of this signal, the one that the TUNZ dot wave. What is the rate at which it was written? What is the sampling rate of this one? So that is the first value in this input. That is the rate. I will show you this. Then wavefile.write is used to write the new sequence. This comp out is the compressed value or a combined value. This I have to write at another wave file. So here that is written as the file name is TUNC combined, comma rate. Rate is the rate at which the original signal was written. Then the file comp out. This is the one that I have to write as a wave file. Of course, I have to make it a int 16, a 16 bit integer. So I have to change the type to as as type int 16. Then of course I can plot this input signal and appreciate this. I can plot this compressed combined signal and appreciate that. Then I plot the characteristics of combander. That is, I put an x-axis from -1 to 1 and plot this ALO combanding for 75, 89 and 100. Okay, 89 and 100, you can appreciate this. Now before you go into this, I will show you my wave file, original wave file. Yeah, I will remove this. I don't want this here. This is my original file tunc.wave. I will play this file. I don't know whether it will be audible in the audio, or it will be audible. I will try anyway. I will try playing this anyway. I will keep the volume very large. Okay, it's already very large, and I will.
The pre-mapping function can be used to ensure that
I'll play it again.
the pre-mapping function can be used to ensure that the
It's an old unfortunate student of mine speaking. Now I will read this tunc.wave and we will appreciate this. First I will open a Python terminal. I don't need this. I'll open a fresh one here. Open in terminal. I will write IPython 3. Not IPython, but IPython 3 I need. Okay, here the first thing is ALO comband.py. I will run ALO comband.py. Now you can see some things happening. Here you can see the your original speech signal. This blue curve is my speech signal. Okay, that the lady was speaking. That short segment of speech, I think it contains only 90,000 samples. Okay, around 90,000 samples. So this is my original speech signal. This blue curve is my original speech signal. Yeah, you can see that here. Earlier I told you there are small amplitude signals as well as very large amplitude signals in the speech signal. Okay, I earlier said that here etc. You can see the amplitude is very small, but here the amplitude is significantly large. Here it is very big. Okay, so giving same step size to both these values, that is not practical. Now I can expand it somewhere, and you can appreciate this. Say for example here I will zoom this. Now you can see this is the speech signal. This is how your speech signal looks like. Okay, and this is the companded signal. Logarithmic compression is done here. Sometimes expansion is allowed. Here you can see that this is a very big peak. You can see that the signal is compressed a lot. Okay, the signal is compressed a lot. So this is how your speech signal appear like. Okay, now I will close this diagram. Now you can see the combining characteristics for different values. Okay, that log function, log mod x by log 1 plus a, that function that looks like this. For this a equal to 100, if I look here, you can see that this is from minus a to a. Okay, minus 1 to 1. You can see that this comes this way and this it goes this way. Okay, here you can see that for small amplitude signals, this is 0 to 1 and this is 0 to minus 1. Okay, my input is normalized from minus 1 to 1. So here if you say for small amplitude signals, here a is 100, so 1 by a is a point not 1. Okay, so point not 1 is somewhere here. This is 0.25, so point not 1 should be somewhere here. Okay, here you can see that this curve, this transfer characteristic or combining curve has a large slope. So my small amplitude signals are very amplified. Now as I go higher, you can see that here for large values of the input, you can see that this saturates a little. This is a logarithmic curve. This saturates a little and it compresses my signal. Compresses my large amplitude signals. Now this for a equal to 100, typically a is 100 is a very popular one. A equal to 75 is there. This is the a equal to 75 curve. This is a equal to 89 and this is a equal to 100. This is symmetric in the negative direction. Okay, this is symmetric in the negative direction. Here you can see that here the slope is very large. Okay, so the small amplitude signals are expanded. Here the slope is very small. So you can see that the large amplitude signals are compressed. Now you can see that my program has written a new file called TUNC Companded. Okay, that's another wave file has been written. Now at what rate I will show you. This inp is my speech signal. You see that it has got two elements in that. One is this 22,050. This is actually 22,050 hertz. It is a rate at the sampling rate. It is a rate at which this signal is written. The speech signal is written. Is converted to a wave format. It is after a compression that it is stored as in the wave format. And the sampling rate used is 22,050. So I should write this at 22,050 back. Otherwise, it will be distorted a lot. So the second one, this is this array. This is my speech signal in integer format in D type int 16. Okay, so that's why I'm very interested in the inp0 value. This is the rate of the sampling. So that is why I inp0, this is my sampling rate. So at the same rate I have to write it back. I have to write my output back, otherwise it will not be audible enough. Okay, here you can see that I write the speech signal here. Where is the speech signal? Where did I write the speech? Yeah, wavefile.write. Okay, so this TUNC Companded has been written here. Now you can play that. You can see that it will be compressed a lot. I don't know whether it will be audible to you. I will remove this thing and I will use the main speaker. So hopefully it will be recorded. So this is my output signal. This is a commanded speech signal. I'll play again. Okay, now let me go back to my presentation. Now these are the results. Already you have seen that this original signal, the blue curve is my original signal, speech signal, and this green ones, small ones, they are the combined signals. This is the combined characteristics. Okay, yellow combined characteristics look like this. Now there is another law for combining, that is a mu law combining. So mu law combinder has the input output relation ship as y mod y, that is equal to log 1 plus mu mod x by log 1 plus mu, where x and y are my input and output signals. So here also I will show you that Python demo. Here is a mu law combined. Here also I have imported all this SciPy wave file and I read the same tunc.wave. So here this is my mu law combiner. It's a straightforward implementation of that equation. Likewise, I read this thing, write, apply commanding to the input signal, write this output signal as a wave file. This is a file I have to write is tunc commanded by mu. Okay, this file will be written when I write this, when I run this code, this new wave file will be written. So everything else is the same. Only thing is, instead of the yellow combining, I use mu law combining. Here you can see that I have this tunc combined I remove. Okay, I don't have any other wave file in this directory. Now when I run this file, when I run this code, run mu, a new file will be written. Now you can see that likewise here also this is a speech signal. This blue curve is a speech signal, and this dotted red curve, there is a combined signal, but by mu law combining. Here you can see that here you can see the effect of that combining, and here in the large peak you can see that the compression is really severe. Okay, you can see that this is really very hard compression. Okay, here in the small amplitude levels you can see that they are somewhat higher, that there is some expansion. Now you can see the combining characteristics here. This is for mu equal to 255. Mu equal to 255 is very popular. So here this is the way it is happening, just like the yellow combining. Here for small amplitude signals, the slope of this characteristic is very high, and for large inputs the slope is very small. Okay, and this is a curve for mu equal to 255. This is a curve for mu equal to 100. This is a curve for mu equal to 75. Okay, mu equal to 50 will be below this. Okay, so this is a combiner character, mu law combiner characteristics. Now you can see that a new file has been written here. A new wave file has been run, tunc combined by mu. Okay, I will run I will run this with VLC media player, and I hope you can hear it in this video. I will play this again. Yeah, it's very difficult to hear that. let me go back to my presentation. Yeah, this is a result of the Milo combining, which you have already seen. This is the transfer characteristics of the Milo combander. And when we come to the practical difficulties, this logarithmic curve, this transfer characteristics, such a system cannot easily be implemented with LTI systems or anything. So with a practical hardware, you cannot easily implement such things. These two ALO and MULO characteristics, this logarithmic function, you cannot easily implement. So what people do is, this is not a practical thing. So we go for a practical implementation of MULO and ALO encoders. So what we do is, instead of this logarithmic curve, a piecewise linear approximation is used. Say, instead of having a continuous logarithmic curve, I will have a piecewise thing. I have one slope here, I have one segment here. This is segment 1, okay, with a large slope. Then a segment 2 with a still smaller slope. I may have a segment 3 with another still smaller slope, segment 4 with a much smaller slope, and a mirror image here in the negative direction. Okay, it is easy to implement such a thing. So here I have 4 segments in the positive direction and 4 segments in the negative direction, making a total of 7 segments, because the central one is contiguous. The central one, the one happening at origin, this segment is contiguous. Okay, so if I can allot different codes to these segments and values coming within the and assign quantization levels within these segments, then I can make a practical ALO and MULO encoders. So this central segment, this contiguous segment has the highest slope. Maybe these are some slope. This may have half of this slope, and this may have half of this slope, and likewise. Okay, so you get an almost logarithmic response. Okay, so here I have 4 segments in the positive direction and 4 segments in the negative direction, making 7 segments, because the center one is continuous. This is 1, S1, S2, S3, S4, S5, S6, S7. Okay, so this way you can do that. That we will discuss in the coming videos. Practical and MULO encoders. Now, coming to the end of this, you understood the need for non-uniform quantization, because we cannot assign equal size steps to both small amplitude signals and large amplitude signals, because both are very important in speech. Then you learn the ALO and MULO companding rules. Then you observe the demo of this combander transfer characteristics. Then you understood the practical difficulties in the hardware realization of these two combanders. Then you appreciated a piecewise linear approximation for the companding characteristics. And that is the end of this presentation. I thank you all.